this, but for this talk, it is a K-linear. So I'll take K to be an algebraically closed field. Not important that it's algebraically closed, but it just makes things slightly easier. I want the endomorphism of the tensor unit to just be the field. Every object should have a dual, so it's symmetric, left and right dual are the same. And it's an abelian category where objects are expected to have finite length. So these are the axioms for tensor category that I'll follow.
Sorry, did you say symmetric means it makes, sorry.
Yeah. So
symmetric doesn't mean that that is not what I'm reading.
Yeah,
I know there's no grading.
No, symmetrically braided. By symmetric, I mean braided.
Oh, okay, well, I was confused.
Yeah.
Maybe I misheard you.
So it's braided where I didn't say braided. But I mean, when I say symmetric, it's understood to be braided in a way that the braiding is corresponding.
The axioms of the tensor category over
It needs to be a symmetric monodal category plus those three.
plus in it. Oh, okay, great.
Yeah, so I mean the structure is a symmetric monodal category, and I'm demanding some properties. So your typical example would be take some blah group and look at blah representations of them. So profinite group, continuous representations, algebraic group, rational representations, abstract group, all representations. There's many variations. They're all examples of this, and they're all in turn equivalent to representation categories of some affine group scheme. So for like a topological group and continuous real representations, there is some affine group scheme of the real number that has the same representation theory. So these are the Tanakian categories, the Tanakian tensor categories. So representation categories of affine group schemes, but they can also be often interpreted as representations of some other type of group. Okay. So I'll start first off by talking about characteristic 0. So we have our tensor category. Its Grothendieck group is a ring because we have our tensor product. But because we have a symmetric structure as well, we can also take exterior powers. So particularly in characteristic 0, where we're at the moment, this is completely unambiguous. I have an action of a symmetric group. I take my skew symmetrizer. It's an idempotent if I rescale it, and I just look at that corresponding summand. I call this the exterior power, works for any tensor category. So with this structure, it's not very difficult to check that you actually get a special lambda ring or a lambda ring, depending on your favorite terminology. So the universal properties are satisfied. So there we go. Tensor categories, in this sense, categorify lambda rings. Let's go with that. So then there's this famous classical theorem, which tries to characterize Tanakian categories among all tensor categories, at least in characteristic 0. So equivalence between 1 and 2 is very classical, doesn't need characteristic 0, and it goes back at least to Grothendieck. So this is kind of the complete statement of what I said. All those types of representations of groups, they're all representations of affine group schemes. Well, this is the most general incarnation of that. As soon as you have some tensor functor to vector spaces, your category is Tanakian. And tensor functor means monoidal, symmetric, monoidal, exact functor, K-linear. So these are kind of extrinsic characterizations. Tanakian means there's an equivalence with some representation category. This means that there is some functor to another category, so they're kind of extrinsic characterizations, but you can do it intrinsically. So as soon as you have the property that for every object there is some exterior power which vanishes, your category must be Tanakian. So one direction is obvious, the other direction is difficult. You can formulate this quite easily as saying that this lambda ring, every element has finite lambda dimension. Well, it's kind of neat that this characterization can be done completely on the level of the Grothendieck ring if you keep track of the lambda structure.
Sorry, what's the lambda dimension?
At just first lambda I which vanishes, or the one for which all above vanish, would be the correct definition. So it's quite literally the same thing. But in some sense, it's quite nice because, and insofar as I know anything about lambda rings, the nice thing about finite dimension is that you can use the splitting principle, which says that you can think about it as some sum of line bundles. And that's precisely what this theorem actually does for tensor categories. It says if all your objects have finite dimension, then there is a tensor compared to vector spaces. So I can kind of extend things and think of my object, which turns out to be a representation, as something which completely splits into one-dimensional things, a vector space. So in some sense, this theorem is a categorification of the splitting principle, if you want, for the purposes of today.
So this lambda dimension is a dimension for an object, right? And do you then extend it to the others?
Yeah, it's so. This is indeed only defined on certain elements, but by the not quite linearity, but lambda 2 of x minus y would be lambda 2 of x minus lambda 1 x. Yeah, there's a unique way to extend it so that you get a pre-lambda ring. Okay. And finally, an equivalent characterization is that every object has a natural categorical dimension. So because I have duals and a symmetric structure, I can define the dimension of every object, which by definition would be an element of my endomorphismal tensor unit, which was assumed to be the field. So these are all equivalent characterizations. Again, here one direction is easy, the other direction is difficult. Okay, so a great theorem. So not all tensor categories are Tannakian. So the simplest counterexample would be the category of super vector spaces. That's Z2 graded vector spaces with the Kossel sign rule. So it's Z2 graded vector spaces, but as a symmetric tensor category, I twist my braiding to induce a minus sign whenever I exchange two odd vectors. And super vector spaces do not form a Tannakian tensor category because this property will fail. If I take one-dimensional odd vector space, then by the sign twist, this will become actually symmetric powers in some sense, and they don't vanish. But again, we can characterize super Tannakian categories. So these would be representation categories of supergroups, or equivalently those which admit the tensor compared to the category of super vector spaces. It's completely analogous. And one way to characterize them is so the exterior power doesn't always have to vanish, neither does a symmetric power, but there is always some short functor which vanishes. So this is some idempotent of your symmetric group of some rank which must vanish. A different equivalent characterization is that it's of sub-exponential growth, which means that for every object, I can look at this function. So for every natural number, I look at the corresponding tensor power. I can measure the length of it, and this needs to grow not faster than an exponential. Obviously, if I have representations of some supergroup, this is some vector space with some structure on it. The length of this will be bounded by the dimension, which is the exponential of the dimension of x. So, again, one direction is easy. And you can also interpret this in K0 because you can formulate in principle all Schur functors in terms of the lambdas. But it's a stupid statement to write out. But again, it can be characterized on the decategorified level. Interesting, it's not sufficient to demand that all dimensions are integers. That would be kind of a naive guess step by analogy, but that's not quite true. So I guess by that statement, I already gave away that not all tensor categories are super Tannakian. So the typical example would be what are often known as the mean categories. which in some sense featured in Alistair's talk. So maybe if there's anything to take away from this talk is I'm suggesting a new notation for these really categories. So people have been using many different notations, often underlying something somewhere, but I kind of concluded that this is a good notation. Because what you do is you look at representations of GLN, you look at the tensor powers that generate everything, their endomorphism rings are given by symmetric group algebras, and then you just mimic that abstractly, and you forget the quotient out. You forget that Schubal duality isn't an isomorphism, and that's how you get this. And then at some point, you need to plug in a dimension, which you do at the end, and that's how you get your T. So that's why I like this notation. And you can do the same thing for the symmetric group. So if T is not some integer, then if you do this procedure that I just described, which would be the oriented Brouwer category, if you take its idempotent completion or the additive and idempotent completion, you get something semi-simple, so actually a tensor category, something semi-simple abelian. If T would be an integer, then you need to take an abelian envelope, which is a lot more intricate to do, but it can be done. So there is also a tensor category for every T here. And they're of super exponential growth, precisely because you forget to quotient out by this relation that you usually get in Schubal duality. So there's another fun procedure, which is using ultra products. Right? So you take some chain of tensor categories, let's say labeled by the natural numbers, and you take some non-principal ultra filter on the natural numbers, and you take an ultra product by the general nonsense, you get again a tensor category. Not quite true. I demanded tensor categories to have objects of finite length. So that will be violated here, because that's not something, I mean, they can be unbounded, so typically in this product they will be going. But often you can find some nice subcategory, typically something generated by one object which you choose in the product. So for instance, if for Cn I take rep GLN, let's say of the complex numbers, and I do this, then inside here I will find this category here, because the ultra product of the complex numbers will be not canonically isomorphic again to the complex numbers. The limit of this n will be some fundamental number, and you get precisely this. So there are some connections. And more recently, Nate Harmon gave a great talk here a couple of months ago about this polygomorphic business. So there's a completely new construction which recovers these ones, but some fundamentally new ones as well, which are really interesting. So there is still a lot going on there, and partly motivated by that, and also partly motivated by kind of some new insights which come from positive characteristic where things are more complicated. I think it's actually a relevant question to ask, does the structure theory end here in characteristic zero? Because that's typically how this is presented, for instance, by myself. As you know, in characteristic zero, you have Tanakian, super exponential growth. Okay, let's move to positive characteristic. But I mean, who says that there's not more structure to be determined? Why can we lump all these ones together? Why is it not the next level and the next level of specification? And like one specific question, which again comes from positive characteristic, as you'll see towards the end of the talk, if you plan on paying attention in the second half, is, are there some of these categories which are more Tanakian or more super Tanakian than others? Doesn't seem well defined, because probably it isn't. And one reason why I think the answer is no in characteristic zero, at least, is that I told you can use rep GLN to get this. You could also use rep GLN plus one supergroup with the same categorical dimension, and you would get the same category. So somehow it seems that in this super exponential growth business, Tanakian and super Tanakian really get lumped together. I don't know how to kind of make it more precise, but yeah.
I mean, if you ask to just change the target of the tensor conqueror, if I just ask, you know, symmetric for tensor categories which admit a monoidal functor to some other fusion category.
Yeah,
I mean, is that? Are you suggesting that for the Fibonacci category, that might not have a particularly interesting answer, or?
Well, yes and no. So the Fibonacci category that will pop up here is in positive characteristic because the one that was mentioned this morning is not symmetric.
Ah, right. Okay.
So it doesn't pop up here. So that's so like this Fibonacci category is kind of prohibited by this theorem here. It says as soon as you don't grow insanely fast, it has to be supergroups, the representations on supergroups. So you can't have these golden ratio dimensions, etc. So a priori, you might expect that such a thing exists, but this kind of tells you that the universe doesn't allow it. But in some sense, yes, because one can propose the following definition. You can say that a tensor category is incompressible if basically you cannot make it any easier. So if any tensor functor to another tensor category is just an embedding as a tensor subcategory, which I tried to formulate here rigorously. So easy example would be vector spaces. You can't have a tensor functor from vector spaces for anything except just an embedding of vector spaces into another tensor category. With a little bit of work, you can see the same thing is true for super vector spaces. And with a little bit more work, you can see that, well, basically the theorems tell you that those are the only ones of sub-exponential growth. So the conjecture first stated by Ostrik is that in characteristic 0, there are no other incompressible tensor categories. So this is in some sense an answer to the question, does the structure theory end here? In some sense, if this is true, it does. You have three choices. You have a functor to vector spaces, to super vector spaces, or not at all. So the conjecture is that there's no incompressible tensor category of super exponential growth. So you can't do this game of classifying them by some nice target.
Is this conjecture like believed, or is it like?
Well, there's a bit of space left on the slide. So what we've proved so far is that there's no tensor functors from red ST to any incompressible categories, which is, but at least we have found something that we can tell for sure. This doesn't go to anything incompressible. So at least it prohibits the idea that everything goes to something incompressible. And I believe it. And I should also say that if we replace GL here, if we take out S and put GL, then this would be sufficient. Because rep GLT is somehow universal. It maps to everything. So if there would be no functor from rep GLT to anything incompressible, there wouldn't be a functor from anything super exponential. So, I mean, aside from two letters, we've already proved it. But it's an important difference. And there's some more reason to believe it, which will appear when we talk about positive characteristic. So I'd say this is believed, but it seems difficult to prove. Okay. So let's move on to positive characteristic. So there has been known for a long time that these linear theorems don't hold. So some of the formulation makes total sense in positive characteristic as well, but they're not true, as stated. Because there are some other interesting tensor categories in the way that I define tensor categories. And the example, like the basic example is precisely the positive characteristic analog of what Ed talked about this morning. So this morning we saw it's interesting to take the Verlinde category for SL2 quantum group. So you can do the same thing for SL2 algebraic group in positive characteristic. So you can look at this category of tilting modules and semi-simplify, quotient out unique maximal ideal, you get something semi-simple. It's a symmetric fusion category. So that's basically the choice you have to make. I mean, you look at quantum in characteristic 0, it's not symmetric, or you look at this thing in positive characteristic and it is symmetric. And if you do the same procedure to the representations of a cyclic group of order P, you get the same category. So this is slightly easier to work with. So if you know a little bit about semi-simplification, you know that the simple objects here are the indecomposable ones in the original category, whose dimension is not 0 or divisible by P. Because we're talking about the categorical dimension. So we're looking at all indecomposable modules except the projective one. They all survive, but the projective one gets killed in the semi-simplification. So the first examples are not terribly exciting. You just get vector spaces in characteristic 2, super vector spaces in characteristic 3. But in characteristic 5, we get precisely this Fibonacci category, which not coincidentally was appeared for I25 this morning in the quantum setting. So the Grothendieck ring of these things are the same in characteristic 0 and in positive characteristic. So in particular, we have also this Fibonacci relation, golden ratio. It can't be super Tanaki. So this is the first example of why the linear theorem don't extend. You can actually also show that the Grothendieck ring of this thing will not be a special lambda ring. So it's still a pre-lambda ring, but it's not a lambda ring. So that's another way of seeing it can't be super Tanakian.
That's wait, I mean, I've never seen a lambda ring before, but so there's no in characteristic 5, there's obviously no lambda 5, or you share sub or
So yeah, so typically lambda rings you said would embed in them, so it wouldn't be an algebra in positive characteristic.
I'm just trying to figure out how you define the operational product.
Well, I mean, it is a pre-lambda ring, and the operator lambda 5 is just a fifth exterior power.
What does that mean?
Yeah. So you just do it in the category, but it is slightly ambiguous. For instance, you can say we look at invariance under a sign twisted action of symmetric group, or the co-invariance, or you could even look at the image of the skew symmetrizer. They all give slightly different answers. So it's but yeah, if you take invariance or co-invariance, you still get a pre-lambda ring, but it just doesn't satisfy the universal properties of a lambda ring. So we get more stuff than just Tanakian and super Tanakian, but it's actually quite fascinating how badly things change, because there exists this whole tower of incompressible tensor categories. So we have P, which contains vector spaces and super vector spaces. Sometimes it's equal to them in a small characteristic, but then it just keeps on going. There is something called P squared, P to the power 3, etc., and they all embed into one another. So the way you get these is by taking tilting modules for SL2, quotienting out not quite a maximal ideal, and then take an abelian envelope. So it becomes much more difficult to do, but it can be done, and they are incompressible. So in particular, you can't have a function from here to there, for instance. Every time you get something genuinely new. So it's only verb P that is semi-simple, that is the fusion category. All the others are not semi-simple. But the reason that they're so fascinating maybe is that here I can't even define this lambda. But by that I mean knowing the image in the Grothendieck ring of an object doesn't allow me to determine what the exterior power will be. So for a vector space, that's not true. If I know the dimension of a vector space, I know the dimension of all its exterior powers. But in these weird categories, that's not true. So somehow you have some entanglement between the non-semi-simplicity here and the non-semi-simplicity of the symmetric group. Okay, so just to kind of end this landering nonsense, in characteristic 0, we automatically always got a landering. In positive characteristic, sometimes you still get a pre-landering, and sometimes it's just not possible to define this lambda at all. It's fine up until p minus 1. I think also p plus 1 would be a problem. I mean, as soon as your symmetric group is no longer semi-simple, problems can and will appear. Okay. So in some sense, the analog of linear theorems is the following. In positive characteristic, the following are equivalent. Your tensor category is Frobenius exact, which I haven't defined yet, and of sub-exponential growth, if and only if it admits a tensor functor to the Berliner category, or equivalently is representations of some affine group scheme in the Berliner category, etc. So Frobenius exact can be, I mean, that's not the usual definition, but the way I build it up, it's more logical to define it like that. It's precisely when lambda p is defined. So that's kind of neat. So it's just lambda p, and if that one is all right, then everything else will be all right as well. That's not completely trivial.
But it's the same meaning as the usual Frobenius exact. It's just a different definition.
Yeah.
Okay. Yeah. So it's not using the word in a different way.
No.
Yeah. Okay.
Yeah. It's yeah. I will give the more classical definition in a second. So this Frobenius exactness, for instance, is automatically satisfied as soon as you have a tensor functor to something semi-simple. Because in a semi-simple world, this will always be fine, and then with tensor functor preserves all properties. So this really tells you that as soon as this, for instance, means that every semi-simple tensor category has a tensor functor to the category. But also that there's no other interesting fusion category to look at from this point of view. And then, of course, the conjecture is that the following is equivalent if we drop Frobenius exactness, your categories of sub-exponential growth, if and only if you have some tensor functor to the union of all these higher vertical categories. But so this is I'd say there's not much evidence for this in some sense. This is very new, these categories. It's the natural analog of this, but I'd say we're very far from proving this. What we did manage to prove recently is the following much more weak statement, which is that if your tensor category is of certain exponential growth, then it admits the tensor functor to some incompressible category. So in characteristic 0, things went the other way around. I mean, linear proved you have a tensor functor to vec or supervector spaces, and they're incompressible, and you're basically done. But here, this is not a priori clear that we were barking up the right tree, like looking for incompressible categories. Maybe it's just not true that everything has some functor to some incompressible categories. So we checked that first, and that is true. So that's a good sign. So basically, the previous conjecture becomes the only incompressible categories are precisely subcategories of that union of Berliner categories. I'm not saying this is easier to prove, but it's a reformulation. So I want to say a word about the strategy of this proof, not for trying to prove this, because it relates back to something in characteristic 0 I mentioned. So the crucial technical tool that we use in the proof of this is that if we have some directed system of tensor categories of sub-exponential growth, then the direct limit, in kind of the naive sense, is again the tensor category of sub-exponential growth. So this might not look like a great statement, but if we drop sub-exponential growth, then such a limit doesn't need to be a tensor category. I mean, it's again a tensor category up to this finiteness assumption. So again, objects can have unbounded length. So in the limit, you'll expect infinite length of objects. But by some magic, for sub-exponential things, this doesn't happen. categories of certain exponential growth, then the limits, everything remains finite and even again of certain exponential growth. So this is a non-trivial observation, and it's crucial for the proof of this because I mean, basically what we do is we take some tensor category, let's say it's not incompressible, that means I have an interesting tensor functor out of it. That one is not incompressible, I can continue, and so I get a whole chain, now I take a limit, and I can continue. So basically you're mimicking the proof of Zorn's lemma. Right, so this is the analog of every union or every chain has a maximum, blah, blah, blah. So we can't quite prove that if you do this construction, you get a partial order, but it's close enough to a partial order that we can bend Zorn's lemma to fit the need. So the reason I'm going into detail here is there's this conjecture that at least the guy is 0. There's no incompressible category of super exponential growth. And this kind of explains a little bit why. Crucially, you can't do this thing. So that's some kind of soft evidence also for that conjecture. Okay. So I want to talk a little bit about Frobenius twists, at least so as to define Frobenius exactness properly.
Yes.
Sure.
In that previous situation, you have the tensor functor do this incompressible thing. Does that mean your category is automatically Synochian? Like,
Yeah,
over the
there's a general principle. As soon as you have a tensor functor to some tensor category, your
it always is.
original one is basically some category of representation of some affine group scheme defined internally or entirely again. Yeah, I didn't quite make that explicit. Okay, so obviously Frobenius twist in model representation theory is very important. We want to define it for an arbitrary tensor category, so we need to kind of make the definition slightly more abstract. So this is one option. You can quickly check that this recovers the usual motion of a Frobenius twist of a representation. You take the image of the canonical map from invariance of the symmetric group into co-invariance. So this turns out to be additive, not linear but additive.
What is this?
So this is the divided power of the invariance under symmetric group, and this is the symmetric power of the co-invariance action of the symmetric group. So in positive characteristic, they're not the same. So depending on your situation, the good or the bad thing about this is that if I take a super vector space, this will kill the odd part. Because let's say we take a one-dimensional odd super vector space, both of these things are 0. So for a vector space, it basically gives you the same vector space, but the same dimension. For a super vector space, that's not the case. So I mean that can be good or bad depending on what you're trying to do. But we could just look at invariance and co-invariance for the cyclic group of order P inside the symmetric group on P symbols. And for a vector space, this will still give you the ordinary Frobenius twist. But also for a super vector space, it will preserve everything because you can't see the sign anymore. So this kind of is a proper Frobenius twist for super vector spaces. It remains monoidal, for instance, for super vector spaces. You can quickly check this doesn't remain monoidal because odd times odd is even. If it kills odd, it should kill even, and it doesn't. So in complete generality, even this will not be monoidal, but you can construct something monoidal which looks like this. This is again the linear tensor product like an n-stop. So basically, what we do here is we favor the trivial representation of the cyclic group. If we also take the two-dimensional, three-dimensional, etc. representation, you can construct a bunch of these functors. So just think of twisting with the representation here, and you glue them all together, and you get something monoidal like this. So this is kind of the full Frobenius twist. And so now a more sensible definition for why it's called Frobenius exact. Something is Frobenius exact if and only if any of these functors is exact. They're all equivalent conditions. So and
this
that
has nothing to do with an exact category that is also Frobenius.
yes, so it
Because that also, I mean, that's the place where I know Frobenius
Yeah,
extract.
okay, I was worried that we were talking about the same thing.
Yeah, okay.
Yeah, no, yeah, it's just,
Yeah, it's a different-
probably this twist
yeah.
which is exact. But obviously for group schemes, this is exact, but we've seen that for arbitrary tensor categories, it doesn't need to be exact. I mean, and the counterexamples are only very recent. Okay. Yeah,
On the growth of the group, or this, snap to like now.
I'll come back to that, time permitting. So, with this stuff defined, I can now actually make sense of this very weird question characteristic 0, because we can define analogs of this, not via the usual, well, and also via the usual construction, but it will be difficult to get something convenient, but with this ultra filters. So this also works in positive characteristic. You can define categories like this. And now the interesting thing is, if I define them using GLN or GLN plus 1, 1, I don't get the same thing. In characteristic 0, I do get the same thing, here I don't. And you can tell them apart, for instance, using these functors. Because if I use this one on the first one, it will preserve everything. If I use it on the second one, it will kind of kill apart. So these two will be the same on the first one, they won't be the same on the second one. So somehow in positive characteristic, even in super exponential growth, there's a notion of being Tanakian, which is weird. I mean, it's weird that it exists in positive characteristic, or it's weird that it doesn't exist in characteristic 0, or both. But not neither.
I quickly double check my understanding. If you take one of these
Yeah.
characteristic, it's changing all the time and it gets like a characteristic 0. That's not.
Yeah, so there's a lot of things you can do. You can take everything in characteristic 0, end up with something in characteristic 0. You can take varying positive characteristic, you end up in characteristic 0. But that's interesting if you want to get rep GLT 14 integer in characteristic 0. Because, yeah, otherwise you can't get to it, because you'll always end up with something transcendental, because it would be a solution to infinitely many polynomials, etc. Yeah, so but here, if you take constant positive characteristic, you will stay in that characteristic. There's a lot of options there. Okay. So then you can ask, and I don't have any idea about how to answer this, does this kind of translate into a nice structure category? Does this indicate that maybe here there are incompressible categories of super exponential growth, which kind of that every Tanakian super exponential goes to? This is all quite open. So at the moment we have such a poor understanding of the sub-exponential growth case that we haven't really looked at this in much detail, but there's so many questions you can ask. So this will say something about one of Ben's questions. So I call this conjecture, you could also ask it, call it question. The following might all be equivalent conditions on any Frobenius exact tensor category. So you could ask that the full Frobenius twist is just FR1, by which I mean it's only this bit which is not 0. Like everything else here, every other component of this thing should be 0. So this will be the case, for instance, for Tanakian and super Tanakian categories. It's not completely trivial, but you can check. This thing is a ring homomorphism. That's quite easy to check that they're the same. You can always define the P Adams operation. Frobenius exact means lambda is defined. It's not necessarily a lambda ring, so this isn't necessarily a ring morphism, but this condition might be equivalent. And then another equivalent formulation is that Frobenius is precisely your P Adams operation, which in some sense answers your question. So on nice categories, this should be a categorification of the P Adams operation. And of course, this implies this, but it seems that the converse might also be true. So The evidence for this is if your category is of sub-exponential growth, you can use our theorem and kind of cheat your way out of it that way. But you can also check it for p equals to 2 and 3 just by slamming the thing hard. And actually there we have no examples of any category that doesn't satisfy any of these. So that's another conjecture that, for instance, for p and p equals to 2 and 3, these are all satisfied. So again, a lot of things we don't quite know, and interesting, sensible questions, it seems. Okay, I still have time.
Yeah,
Okay,
something like nearly 10 minutes.
okay. So I probably don't have 10 minutes left, but
8.
okay. Well, this is going fast. So how can we intrinsically determine when a category is incompressible? So we've seen these examples of incompressible categories with this conjecture that they list all of them. In characteristic 0, we only have 2 incompressible categories, vector spaces and super vector spaces. It doesn't quite make sense to ask the question, how do we characterize them intrinsically? Well, either as vector spaces or super vector spaces. But here you can ask the question, like, how do you tell whether a category is incompressible intrinsically, not by just this definition of every tensor vector out of it is an equivalent. So one step in that direction is this nice proposition. So if a finite tensor category, finitely many simples, and we have projectives, in which case it is a Frobenius category, but that's the wrong Frobenius. If it satisfies this property, so the Gelfand-Grillo dimension of every symmetric algebra is equal to the dimension of the Hom space from X to the tensor unit. It's not quite clear why this should be something interesting, but if this is true, then you can prove the category is incompressible. So by this, I mean, you just take the growth rate of this symmetric algebra, for instance, using the length of the object or the Frobenius Coulomb dimension. And you can quickly check that this is a lower bound of this. Like if the vector space obviously needs to be the same. The dimension of the space is the Gelfand-Grillo dimension of the symmetric algebra. And you always have a surjection from this symmetric algebra onto the corresponding symmetric algebra of the maximal vector space that is the quotient of your X, which gives you a bound for the Gelfand-Grillo dimension. And if you think of super vector spaces, then the thing about super vector spaces is that every odd thing is nil potent in commutative sense. So for a super vector space, this will be true. It's only the even bit that will contribute to the Gelfand-Grillo dimension, because the odd bit will be just the exterior algebra, which is finite. So you can check that this is satisfied for vector spaces and super vector spaces, but also this gives you a sufficient condition to have an incompressible category. Something you need to prove, but it's not too difficult. So it would be great if at least we can check that this category or its finite subcategories satisfy this thing. So we've been able to do that for characteristic 2, which is hopeful that maybe this could characterize incompressible categories. It's sufficient, and it's conjecturally sufficient for p equals 2. So for p equals 3, we've got up to 9.
Mm-hmm.
And for p bigger, we got up to 1. So it seems very difficult to check. This is the model here. Okay, I think I'll finish there.